Okay, friends. So we'll start with the PV system design. PV system design based on load requirements. So let's see what are the load requirements, and based on that we'll design the PV system. So for that, first we'll see some generic steps that should be followed for designing of PV systems. It's a simple approach which includes many assumptions. So it's not a detailed approach. Now the first step is to determine the total load current. The total load current and operational time. So if the operational time per day is given for the particular load, so based on that we can find the operational time and load current. So basically this is in amperes and this is in hours. So what we need is to find the ampere hours, right? Now the second step, add system losses. So we should design the capacity so that it can compensate for the network losses also. So we should know about the we should have an idea about the system losses in terms of percentage. That is enough. Then third one is determine the solar irradiation. The solar irradiation in daily equivalent sun hours. Daily equivalent sun hours, because it's important that where are we installing this panel. So according to the location, we have the solar irradiance data. So based on that we can have the daily equivalent sun hours of that particular location. So daily equivalent sun hours is ESH. Okay, ESH. We'll see what is that. Now determine the total solar array current requirement. Determine the total solar array current requirement. Based on that we can we can decide how many panels should be connected in series and how many panels should be connected in parallel. You should know the voltage requirement also, the rated voltage requirement also. Now the fifth step is determine optimum module arrangement. Determine optimum module arrangement. Okay, then sixth one is determine battery size. So battery size is based on the recommended reserve time. Based on recommended reserve time. So even though panel is not available, we can use the battery for a particular number of hours. So based on that requirement we can, that is what is the reserve time. Based on that you can size the battery. Now we will see an example with a load requirement, and we'll see how the PV system is designed. Okay, now let's see the data. So I have 4 loads, A, B, C, D. Now A and B are DC loads, and C and D are AC loads. I will give you more details about these loads. So first I'm going to deal with the DC loads. I'm going to deal with the DC loads. So let's see the requirement. So a 12 volt PV system has to be designed. It has two DC appliances A and B, and these DC loads are rated at 15 and 20 watts of power. Then the average operational time per day for these loads is 6 hours for A and 3 hours for B. Now the first step is to find the daily energy requirement of the devices expressed in ampere hours. This is what we are going to do. Okay, now how will you find? So for device A, 15 watts into 6 hours equals 90 watt hours. Then device B, 20 watts into 3 hours equal to 60 watt hours. Okay, so what is the total now? So I'm dealing with DC loads only now. Okay, so total watt hours equals 150 watt hours. By adding these two, you will get 150 watt hours. Now we know the voltage rating, which is 12 volt. The PV system should be designed for 12 volt. So at 12 volt, we can find the ampere hours for this 150 watt hours. So this 150 watt hours when divided by 12 volt will give you 12.5 ampere hours at the output of the panel. This is the requirement for these two loads, these two DC loads. Now coming to the AC loads, what will you do with AC loads? What is the difference? I'm going to do the same for AC loads. Say your appliance C is a computer and your appliance D is a TV set, and they are connected to the same PV system which is going to be designed. The computer has that means device C has a rated power of 40 watts, and it runs for 2 hours. Okay, 2 hours, and the device D has a rating of 60 watts and it runs for 3 hours per day. So we can convert this to watt hours. Here it will become 80 watt hours, and the second one would be 180 watt hours. Okay, now the total is 260 watt hours. Now based on this, we need to find the DC requirement in terms of ampere hours, but this is at the AC side. So we'll have an inverter which converts DC to AC. So at the panel output side or the inverter input side, it will be DC and we have to convert to that side. So to go to that side, we need to know the inverter efficiency. So if the inverter efficiency is considered as 85%, it can be anything. So the thing is we have to use this efficiency to find the ampere hours in DC equivalent. So here it's efficiency of inverter, okay, which is 85%. So in that case, this 260 watt hours can be divided by 0.85. We now move on to the input side of the inverter, which is equal to 306 watt hours. Okay, now we can find the equivalent ampere hours in the DC side. That is 306 watt hours. Whatever we have done here, the same thing, 306 watt hours divided by 12 volt, which will give you 25.5 Ah. Okay, so this is what. So both we have found out now. For the DC loads and AC loads, we have found the ampere hours 12.5 and 25.5 Ah. So the total is, what is the total? 12.5 and 25.5 will give you, 1 minute, let me go to the next page. So now we have to add system losses also, as we have mentioned here. The second step is to add system losses. Then only we can design the capacity of the PV system. This includes loads only. So loads plus losses we have to take. So loads 12.5 Ah for AC for DC and 25.5 Ah for DC and 25.5. This is for AC, but this is in DC equivalent. Okay, so the total DC requirement is 12.5 plus 25.5. And if we know that the system losses are 20%, then into 1.2, I'm taking into 1.2, which is equal to 45.6 Ah. So this is the total requirement, loads plus losses. Okay, with 20% losses. Now we have to determine the solar irradiation in daily equivalent sun hours. Okay, because the energy a PV module delivers, it depends on several factors based on the weather conditions of that location, then seasonal changes, and it depends on the installation of the modules also. The modules can be installed with a tilt angle, or it can be horizontal. So in different angles, it will give different performances. So it is also important to know whether a PV system is expected to be used throughout the year or only around a certain period of an year. Now, in the PV community, one equivalent sun implies solar irradiance of 1000 watts per meter squared. This value corresponds to the standard at which the performance of solar cells and modules is determined. Now, that is the rated parameters of the modules are determined at the solar radiance of one sun. Okay. Now we'll see an example. Say in Netherlands, the average solar irradiation is 1000 kilowatt hours per meter squared. According to AM 1.5 spectrum standard, it's an American standard based on the weather conditions. So for standard weather conditions, one sun delivers 1000 watts per meter squared, which is equal to 1 kilowatt per meter squared. So now we can find in Netherlands what's the annual solar irradiation in hours. If we want it in hours, which is equal to 1000 kilowatt hours per meter squared divided by 1 kilowatt per meter squared, which is equal to 1000 hours. Okay, so this is the Dutch average annual solar irradiation when the annual solar radiation is 1000 kilowatt hours per meter squared, and when one sun delivers 1000 watts per meter squared, which is equal to 1 kilowatt per meter squared. So 1000 equivalent sun hours. This is 1000 equivalent sun hours. Okay, this is 1000 equivalent sun hours, which is this one, equivalent sun hours. Okay, that is what we mentioned in the first slide. Equivalent sun hours here, daily equivalent sun hours we need. Okay, so based on that we can basically the duration in which the panel can produce power, that is what is the meaning in layman language. So 1000 equivalent sun hours corresponds to 2.8 hours per day. Okay, now okay, so we can note the for the PV system design which we are doing now. For that we'll take the value 3 hours per day. 3 hours. Okay, so the daily EHS, for Netherlands, say we are doing the installation in Netherlands is 3 hours per day. 3 hours per day. Now the required total current, we need to find the required total current. Generated by the solar array, generated by the designed solar array. What's that? The total ampere hour requirement is 45.6 Ah, including the system losses and loads, right? So divided by 3 hours, this is the equivalent daily EHS. So divided by 3 hours, it will give you 15.2 amps. Okay, so the current requirement is now known, right? It is found. Now the required total current generated by the solar array is for 15.2. Say if the panel rating is 3.15 amps. 3.15 amps. Panel rated current, let it be 3.15 amps. In that case, the number of modules in parallel, we can find the number of modules in parallel because the total requirement is 15.2. So 15.2 divided by 3.15 will give you 4.8. But 4.8 panels cannot be in parallel, which is less than 5 modules. 5 modules. For one module, the rated current is 3.15. 15.2 is the total current requirement. Now the nominal voltage is 12 volt, right? And if the nominal voltage rating of one module is also 12 volt, then the required number of modules in series will be 12 by 12, which is equal to 1. Okay, one module. Therefore, the total number of modules in the array can be 5 into 1, which is equal to 5 modules. 5 modules. Okay, so this is what is the optimum module arrangement for the designed solar array. Now we have to find the battery size for the recommended reserve time. So what is the recommended reserve time? Let's see. The total DC requirement of loads plus losses is 45.6 Ah, right? And that is per day. If the recommended reserve time capacity for the installation in Netherlands, say it is 5 days, then the total battery capacity, this is for 1 day, right? So the total reserve capacity should be 45.6 Ah into 5, which is equal to 228 Ah. Okay. Now, if the battery is only used for the minimal capacity of the batteries, if it is recommended to operate the battery using only 80% of its capacity for the life of battery. Okay, for getting a longer life for the battery, if it is recommended that the batteries are operated only for 80% of its capacity, then this 228 Ah should be divided by 0.8 to get the total capacity of battery for safe operation. So the minimal battery capacity for a safe operation is 285 Ah. So this is what is the PV system design. So what all things now? Let's once again go through it. First, determine the total load current and operational time. So it can be in watt hours initially, then later we'll convert it to DC ampere hours. So if it is AC load also, we are converting this to the DC side using the inverter efficiency. Then we add the system losses also. So if this is some say if it is 30%, then this the total DC ampere hours would be multiplied by 1.3 if it is 30%. Okay, so we'll get the total requirement, AH requirement. Then determine the solar irradiance in daily equivalent sun hours for that particular location. Then determine the total solar array current requirement. Based on the current and voltage requirement, we see the optimum module arrangement, how many modules are in series and how many are in parallel. Then based on the recommended reserve requirement, we find the battery size, and not only based on the recommended reserve time, based on the percentage of capacity that should be used from the battery for safe operation. So based on these two things, we will find the battery capacity also. So that's all with PV system design. Thank you.